Okay, today we're going to talk about inverse functions, but before we start on the inverse functions, let's recall what a function is. And in order for a graph to represent a function, or in order for something to be a function, that means that there is a unique y value for any or every given x value. So no matter what I put in for x, whatever you're crunching, whatever operations are going on, it spits out, or I get this output of a unique y value. That is a function. And then a one-to-one function was something that has essentially the opposite of that as well. So if I have a unique value of y for any x value, a one-to-one function also, so it has that as well as a unique x value for any y value. So they are all unique. If I put in an x, I get a unique y. If I put in a y value, I get a unique x value. And horizontal line test is an easy visual way to check the graph to see whether or not it is a function. To check if I want to see a function, I use the vertical line test. And to see if it is a one-to-one function, I use the vertical line test first, and then I also use the horizontal line test. Which is exactly the same as a vertical. So if you think about any graph, we'll do a real simple one here. We'll just do a linear equation. So if I just have this linear function here, if I do a real short vertical line test, I see that none of these intercept more than once. And then if I do the same thing, so that's verified it's a function. If I do the same thing this way, this is the horizontal line test, I see none of these intercept it more than once as well. So this is a one-to-one function. And what you're going to come to find out here is that a one-to-one function also tells me that the inverse of this function is also a function, which doesn't always occur. So let's take a look at some examples here. Okay, so let's take a look at these two. We're going to explore their graphs. So I'm going to bring up my calculator here. Go to y equals graph x. I'm going to raise it to the fifth power. And when we graph this, it's a little distorted here. So let's kind of zoom in right in here. So we'll say zoom 2. And clearly we can see this passes the vertical line test. No lines to intercept here. It appears to be very close, as though it might go horizontal here. So let's double check, and we'll look at the table, and we'll look at our values to see if indeed it does. And we see for all of these x values, I am getting different y values. All these y values are producing non-repeating x values somewhere right in here. So let's go even a little closer. Change it by 0.1. We'll just start at -1. And I see still none of these are repeating the x values. So this does appear, while it looks difficult when looking at the graph, but this fifth degree polynomial is a one-to-one function. And we'll look at the second one. And I'll plug in 9 times x raised to the 6th. And we'll get rid of this guy. Minus 7 x to the 5th. Whoops. Minus 4. go back to a standard viewing window, zoom 6. And we see this one right here. It's a 6th degree polynomial. It takes on a similar basic shape to that of a parabola. So it's kind of doing a little U thing here with a little hiccup at the bottom. But certainly if I were to draw lines for this, it would pass the vertical line test. So it is a function, but it does not pass the horizontal line test. Just so that we're clear on what I'm talking about, let's take a little closer look on here. We'll pull up a larger screen. So again, it passes the vertical line test, but if I were to draw horizontal lines, use a better color, I see anything through here has points of interception at there and there, there and there. So these all intersect at twice. So this would not be a one-to-one function. So that's what we're trying to determine with the graphs. Okay, inverse functions. So a function has its inverse, or I know that two functions are inverses, or that two relations are inverses, if and only if for every relation, or any relation of, say, a, b, so some value and some other, its inverse would be, or is, BA. So the inverse of a relation is simply flipping the coordinates. If it were xy, that would be yx. Inverse of a function ultimately works out to be the same thing. Any point on that function, its inverse is simply the opposite of those coordinates. So if you have a coordinate at -7, 2, its inverse is 2, -7. Now you might recall that when you flipped x and y, that actually created a reflection over the line y equals x. And indeed, if you're looking at the graph of of a function that's inverse, you will see that they are reflected over this line, y equals x. That's your parent linear function, runs about like that. So let's take a look at the examples here. So when I look at this function f of x equals 3x minus 11. Oftentimes it's easier if we get rid of the function notation, write it as y equals instead of f of x, or the function notation g of x, or whatever they choose to use. This just makes it easier for us visually to see the swapping of x and y. So what they're saying is if I have this function and f of 2 equals -5, and so when you plug in 2 here, you get 6. 6 minus 11 is -5. So this is actually a coordinate. This is 2, -5. I put in, I have an input of 2 for x, and I get out -5. So that's my relation there, the coordinate on this function. So the inverse of that is pretty simply found. It's just switching, and it's -5, 2. And again, if you graph those two, you're going to see that they are a reflection over y equals x. Big key there to identifying inverses or inverse relationships when you're looking at graphs. It's a reflection over this line. So let's take a look at some graphs. So it's not that difficult to do these. We'll just pull up the calculator. Or I could also just make a little table. We'll plug in this. F of x is 2x plus 5. Excuse me, 2x squared plus 5. And with what we just learned about the transformations, you see we've got this quadratic. It's ultimately amplified, or it's stretched by a factor of 2, and then it is slid vertically up 5 units. So it creates this. So if I go to my little table here, I'll switch this back. We'll just start at 0, go by 1s. I can easily plot some of these points. So if we look, I have 0, 5, 1, 7, negative 1, 7. So we'll just plot a couple of those. So I'll go 0, 5, 1, 7, negative 1, 7. And it goes 2, and it's up here at like 13, negative 2, 13. So it looks something like this. Well, again, remember, we talked about an inverse being a reflection. Well, that is going to reflect over that line, y equals x. So we have a basic understanding of what that's going to look like. And again, if I think of this in terms of a table of values, I just plotted this one, a couple points. I had negative 1, so let's go out to negative 2 here. Negative 2 was at 13, negative 1 was at 7, 0, 5, 1, 7, 2, 13. So then the inverse f of x, all I'm going to do is flip these. Then I'll plot these. So we'll go over then to 5, and we're at 0. Use a different color. We'll do this one in red. I'm at 7 and 1. 5, 6, 7 up here at 1. I'm at 7 and negative 1. And then I'm at 13 and 2 and negative 2, so 10, somewhere out here. And we're at 2 and negative 2. This one looks like that. And again, if we were going to test this on the horizontal line test, we see that clearly it does not pass. I have 2 points of intersection, which tells me that its inverse is not a function. And if I check the inverse for the vertical line test to see if this is even a function, it does not pass that test either. So that's what we can do on a graph. Very easy using coordinates. Visually on the graph, remember, it's just a reflection over y equals x. And using coordinates, all we do is flip the x and y. So if I want to check these algebraically to see if they're inverses, what you're going to do is if you have two functions, you're going to basically take them and supplement one into the other. This goes back to your composition of functions, and ultimately what you're going to do, you're going to take f of the inverse f of x, and that should equal, you should get the same thing as inverse f of f of x. And this will all break down. Ultimately, they should cancel each other out, and you're just going to be left with x. So it's back to our composition of functions. You take the original, you take the inverse, I'm going to supplement this value in here for x. I'm going to do the exact opposite. I'm going to take this in here for this x, and ultimately it should all cancel each other out, and I'm just left with x. So we'll see and check these to find out if they are inverses. Okay, so first let's start by taking this one, and we'll plug it in here for x. So I'll rewrite. So I have 3 times the 1/3 x minus 4/3, all of that plus 4. So what happens here is I'm going to get 3, this has to be distributed, over 3 times x minus 12 over 3 plus 4. Then 3 over 3 reduces to just x. 12 over 3 is minus 4 plus 4. These two cancel, and you're left with just x. And then we'll do the exact same thing, but now I'm going to take this, I'm going to plug it in for that guy. So I have 1/3 of 3x plus 4 minus 4/3. So again, we distribute this through. 1/3 of 3 is 3/3. And then 1/3 of 4 is 4/3 minus 4/3. This is 1 plus 4/3 minus 4/3. This cancels, and I'm left with just x. So these two are inverses. And if we graph these both on our calculator, we can do that here real quick. We should see that they end up being a reflection over y equals x. And there we go. And if I wanted to even put in my line y equals x, and maybe I'll change this so that it's dashed or dotted. And I didn't dot very well, but you see these are actually a reflection over that line. Okay, so in order to verify if these are inverses, I'll take this and I'll plug it into the x values here. So I have 3x plus 5 over 1 minus 2x, that is all minus 5, over 2 times 3x plus 5 over 1 minus 2x, and all that plus 3. So now we have a little work here in order to begin to simplify this down. So I'm going to go ahead and let's distribute this through first. So I get 3x plus 5 over 1 minus 2x minus 5. All that over this. We'll just take that through to the top values. 2 times that is 6x plus 10 over 1 minus 2x plus 3. So we'll go ahead and combine these. So in order to subtract 5 from this, I need like terms. This is ultimately just a fraction, so I'm going to find a common denominator, which would be the 1 minus 2x. So if I do that, I'm just multiplying this by that value. So I can kind of simplify this to 3x plus 5 minus, and then times this quantity. So it's going to be minus 5, and then 5 times negative 2x is a minus 10x. And all of that is over 1 minus 2x. And do the same thing here on the bottom. So I have 6x plus 10 plus 3 times 1, and then minus 6x. And now I can begin to do a little bit more reduction here. So let's go ahead and distribute that through. So that's going to be a minus 5 and a plus 10. That. Okay, so if I drop this back down over here, I've got 3x, 10x's, that's 13x. 5 minus 5, those cancel. So I've got 13x over 1 minus 2x and all of that. Sorry, I should have brought this up. 13x over 1 minus 2x. All over. And then if I do a little combination here, sorry, this still should have been over 1 minus 2x. 6x minus 6x cancels, and this is just 13 over 1 minus 2x. So now I've got 13x over 1 minus 2x divided by 13 divided by 1 minus 2x. Well, remember, ultimately what I'm doing here is I'm dividing by a fraction divided by a fraction. So to cancel that, I would just multiply by its reciprocal. And so what you see happens here is these end up canceling. My 13's cancel, and I'm left with just x. So that took a little bit of work there, but ultimately it did break down to just the value of x. Now we need to check it the other way. So we'll clean this up just a little bit. And now we'll take this value and plug it in for these x's. So I have 3 times x minus 5 over 2x plus 3. That's plus 5, and all that over 1 minus 2 times x minus 5 over 2x plus 3. And then we need to go ahead and distribute through here. So I'll write that back over here. So I get 3x minus 15 over 2x plus 3. Let's go ahead and involve this at this step here. So in order to add 5 to this, I need a common denominator. And the easiest way to do that is to just multiply this by that denominator. So I'm going to do that, and I'm going to combine this with 10x plus 15. Extend that out all over 2x plus 3. All I did was ultimately kind of scale that up by this denominator. And then this is over, and I'll distribute this through 1 minus 2 times x, and then 2 times x, and then 2 times negative 5. And this is over 2x plus 3. And again, in order to deal with this, I'm going to need to go ahead and multiply this by the denominator, plus 3, all over that. So we'll do a little bit of consolidation here. We'll combine these like terms. I got some 3x's here with 10x's. I got some 2x's here with these two. 15 with this 15. 3 with this 10. And we'll go ahead and simplify a little bit. So I'm just going to bring this down right here. So I have 3x's, 10x's, 15's you see cancel, minus and plus. So I have 13x over 2x plus 3 over, and then 2 minus 2, those cancel, 3, and excuse me, this should have been distributed, so this is a plus 10 in parentheses here, and then we distribute the negative sign through. So, and I have 3 plus 10, so I get 13 on top over 2x plus 3. And again, we multiply by the reciprocal. 2x plus 3 over 13. My 13's cancel. My 2x plus 3 cancel. I'm left with just x. So indeed, these are inverses. Again, we can always verify. We'll pull up the calculator once more. In the calculator. This is where the stacked fraction becomes very useful, as we have these rational functions. So I have x minus 5 over 2x plus 3. And then 3x plus 5 over 1 minus 2x. And I'll leave this in there. So there's one of them. There's the second, and indeed they appear to be mirror images of each other. So graphically, we can certainly test them here. I could go look at the table, and I could see that these values. So let's take, like at negative 7, 2, and I should see when this is 7, this one is negative 2. And there we have it. 5, 0. So I should see when this is 0, this one is 5. And we see that there. So you can do it very easily on a graphing calculator, and then to check them algebraically, you use your composition of functions and sub one into the other, and they should both cancel down. It all whittles down to just x. In order to find inverse functions, what we're going to do here, along the same lines of what we've already talked about, for every value of xy, there is yx. So what we're going to do is replace, or if I write this in terms of steps, what I would do first is get rid of the function notation. So replace f of x, or whatever they're using, with y. Just plug y in. It just makes it easier for us. And then we'll go ahead and flip x and y, and then we solve for y. So here's 1, 2, 3. And you'll see what that looks like. So get rid of the function notation, just put in y, it just makes our life simpler. And then we switch or flip the x and the y, we change them. Change the x to the y, y to the x, and then we solve back for y. That finds us the inverse. So if I'm looking for the inverse of this function, first step, I'm going to get rid of this, I'm just rewrite it. Y equals negative 2x minus 7. Now the second step is I'm going to take these two, I'm going to interchange them, I'm going to switch them. X equals negative 2y minus 7. Then the third step is I need to solve back for y, so I need to isolate him. So this is an equation, use your same properties. I'm going to add 7, we'll rewrite this out, x plus 7 equals negative 2y. I divide by negative 2. And I get y equals x plus 7 over negative 2. I'll write that back over here. So there is my function, f of x, negative 2x minus 7. And here's my, I want to change this back, inverse f of x. Let's look at one more example. So again, first step, I'm going to get rid of this function notation. I'm going to rewrite. Okay, now I'm going to change the x and the y. So I put x here, I put y plus 2 over 3y plus 2. Now I have to solve for y. So I need to isolate these guys. So what's the first step again? Well, I need to get rid of all this stuff in the denominator. Go ahead and multiply both sides by 3y plus 2. Those will cancel. So I have 3y plus 2. And we'll rewrite this. Now I need to get rid of this x, or excuse me, the 2. So I subtract 2. Okay, so I'll go ahead and expand this. So this has to get distributed through. So I get 3xy plus 2x minus 2 equals y. Now this is close, but I still have this y over here. So what I'm going to do is I'm going to bring this over. So I'm going to subtract 3x. So let me give myself a little more room. I'm going to write it up here. So now I have 2x minus 2 equals y minus 3xy. Then what this allows me to do is ultimately I've got two terms here, both containing a y. So I'm going to factor out that y. So I have 2x minus 2 equals y times 1 minus 3x. Because when this gets distributed, I get y minus 3xy. So now this y is all by itself. I just have to divide by this. So I get, I'm going to flip these and I'll put y equals, let me go back to the inverse then. This was g, sorry. And that equals, then I have 2x minus 2 over 1 minus 3x. And this is the inverse of that. Okay, bring any questions with you to class tomorrow, and we'll get a little bit more practice.